of isoelectronic. That was not the right button. So isoelectronic really just means same electrons. So let's go through and take a look at a couple examples here. Let's pick oxygen. What is the electron configuration for oxygen? Electron configuration, not its charge. So this means oxygen has how many electrons? How many electrons does oxygen have?
6.
Try again. It has 8 electrons. How many valence electrons? 6. Answer the question that's asked. You have to be very, very careful with this. Okay, so oxygen has 8 electrons. Where does the first electron go?
1s.
The 1s orbital. How many electrons fit? 2. Next orbital. Next orbital. 4. So this is now your electron configuration. Right? Within this, we can do a couple different references. Number one, we can look at the valence electrons, which will become super important when we're looking at Lewis structures. Give me a sec. After that, we also have our core electrons down here. It is possible that we could now go through and simplify our structure by looking at the core electrons and saying, well, really the core electrons is just the configuration for helium. And I could write this electron configuration as such. Okay, everybody okay with that? Hi, what was your question?
Is like just do you have to write oxygen semicolon in front, or?
The semicolon is just to differentiate it. That's not a big deal.
Yeah.
Don't worry about that. Okay, so that was our electron configure, and now I'm going to end up, oh, man. Fine, just erase the whole thing. I said 1s2, 2s2, 2p4. Okay. Now I want to know the electron configuration for, any guesses? Neon. What is the electron configuration for neon? How many electrons does neon have? 10. Where's the first electron go? 1s2, 2s2, 2p6. How many electrons can fit into the p orbitals? 6. So if we look at the electron configuration for neon, and when we think about bonding, what we are trying to do is have it share electrons with another element. Does neon have any desire to gain or lose electrons? No. What does that mean for its reactivity? Almost non-existent. Neon does not want to react with anything, okay, because of that full octet. Or sorry, let's not say that. The full p orbitals. Right? For this reason, that entire column, our noble gases, is entirely unreactive. Okay? Can we make them react? Yes, absolutely. Don't stress about that. Worry about that 151. Okay? That is why when we look at the charges for our noble gases, ultimately, how do they change their reactivity when we bring in another element? Their charges are all 0. Because do we bring in another element? No. So 0 interactions with those. What happens if we now move to, say, oxygen? If we look at the electron configuration for oxygen, what's going on with its configuration? If we look at that absolute highest energy orbital, our p orbitals, it has 2 empty slots. What could we put into 2 empty electron orbitals? Electrons. Good answer. Okay. By putting those 2 electrons in, I can become like neon. So by changing the outer cloak of the atom of oxygen, it can now start to look like that super stable molecule that interacts with nothing, our noble gases. So what happens when we look at oxygen when it interacts with another element? Well, it says this, stupid eraser. this sucks. I want to look like the noble gas. To look like the noble gas, what do I have to do? Green was probably a bad color choice. Let me try that again. To look like the noble gas, say that again. I need to add 2 electrons. By adding 2 electrons, what has happened to the oxygen? Okay. We can look at its electron configuration. We'd say its electron configuration is more stable because it's now fully saturated. We can also reference something about the balance of protons and electrons in that atom. Is it now just an oxygen atom? No. By gaining the electrons, we have changed its chemical nature from being an oxygen atom to an ion. In particular, what type of ion? Anion. Name that anion. Not oxygen ion, it's oxide. Okay, our anions get that IDE ending. So if I now go through and fix this, I keep doing that. I'm no longer looking at the electron configuration for oxygen atom. I'm looking at the electron configuration for oxide, oxygen minus 2. When we're now referencing isoelectronic, the oxide ion is isoelectronic with neon. They have the same electron configuration. That's all that term means. We can use this to predict the charges. All we're looking at is how do we make it look like a noble gas? Could oxygen have looked like other noble gases? What would I have had to do to make it look like another noble gas? Say it again. I could add or take away more electrons. So if I wanted to look like, what's the next one? Argon, what do I have to do? I have to add 2 more electrons to the 2p. Then I also have to add 2 more electrons to the 3s. And I have to add 6 more electrons to the 3p. I can absolutely look like argon. To do that, what did we have to do? We had to add...
Sorry, 10.
I thought it was 8. It didn't sound right. 10 electrons. Okay. Is that going to be an easy thing to do? No. Because that is so difficult, we rarely see oxygen having gained, I already forgot the number, 10 electrons. We would never see an oxygen at a negative 10 charge. Okay. It's still theoretically possible, but the likelihood is very slim. What else could oxygen have done? I could have tried to make it look like the element above helium. To do that, what has to happen? I need to get rid of, here's my fancy emphasis here, all of those electrons. I have to lose 6 electrons to look isoelectronic to helium. Okay, well, with these 3 options, lose 6, gain 2, or gain 10. What's the easiest? Gain 2. What happens? Oxygen takes a negative 2 charge every time it bonds. Okay. What about our halogens? Okay, they're only going to gain 1. Why? They're right next to the noble gases. It's very easy just to add 1 electron as opposed to, in the case of fluorine, losing 7 or gaining 9 to look like argon. Okay? Make sense? Okay. Let's do one more quick test on here. So that explains the rightmost part of the periodic table, but what about the leftmost part of the periodic table? What if we were sodium? 1s2, 2s2, 2p6, 3s2, 3s1. What can it do? If it loses that 1, it looks like neon. Or it could gain 1, 3p6 to look like argon. Okay. We are always trying to look like our noble gases. So what are our options? Lose 1, gain 7. What's easier? Lose 1. What happens? It loses 1, and it carries now a positive charge because the balance of protons and electrons has changed within the atom. Okay? Kind of makes sense? Kind of seeing some silence here, so it's making me a little bit nervous. Are you guys like, okay, we already got this a long time ago, or is this, you're now cool with it? Meh, some hands up, some hands down. Okay. If you don't like electron configurations, accept the point loss. What do you do when it comes to charges then? Rote memorization. You are responsible for those charges. You need to know them. However you decide to learn those charges is up to you. If it's just straight memorization, column 1 is a +1, column 2 is a +3. Okay? Column 13 is a +3. Column 15 is a -3. Column 16 is a -2. 17, -1. If you want to just memorize it, great. Okay. I try to set you up with the background on where these things are coming from. That's the whole point of our electron configurations. That's what we're talking about when we look at isoelectronic. Questions? Why do we not expect you to memorize the charge on carbon? If we look at the electron configuration for carbon, what happens? To look like neon, it has to gain 4 electrons. To look like, what's the next one? Helium, it would have to lose 4. Well, which is easier? Gain 4 or lose 4? Either way, it's a toss-up, which means we don't know. The structure would have to give us more information about what charge our carbon would be carrying. Okay? That's why we don't have you memorize that column. Questions about that? Don't look so depressed, guys. Geez, it's just chemistry. Okay. We already saw the summary, so you can close your eyes so you aren't getting blinded by all that. Electronegativity. Super, super important concept. Okay. This is a definition defined by Linus Pauling telling us about how an atom attracts or does not attract bonding electrons. This is what drives our rules behind Lewis structures, okay, or at least the rules as I have defined them. If you listen to anybody else, their rules make no sense because they have no logic behind them. The logic has to do with how an atom holds electrons. That's how you should be drawing your structures. So electronegativity is a huge, huge concept. Anybody that has to move into organic chemistry, you must understand this. Your most electronegative is found sort of in the upper right-hand corner. It is fluorine. Why none of the noble gases? Kind of. Why does stability have anything to do with it? What is our definition of electronegativity? The ability to hold big capital letters. Bonding electrons. How many bonds do our noble gases make? None. Which means, should they apply to electronegativity? No, because by definition, they don't form bonds. Okay? That is why we ignore our noble gases. So fluorine is our most. Our least is the lower left-hand corner. On this table, we're only looking at cesium. You'll notice that bottom row has not specified any electronegativities, I see it. Any guesses as to why? What's in that bottom row? All of our man-made elements that are incredibly unstable. Okay, well, if they're unstable, can we even measure them for a significant amount of time with how they interact with other atoms? No. If we can't make that observation, we can't come to conclusions about electronegativity. Okay? You'll also notice through the transition elements, okay, it gets all sorts of weird with the transition elements. Okay? And if we try to use electronegativity rules with our transition elements bonding to each other, it turns into a big mess. Okay? Thankfully, we don't worry about it, because if we bound chromium to, say, iron, what kind of bond would we have there? Should be a very hard question. Chromium is a metal. Iron is a metal. What kind of bond do we have between a metal and a metal? You should all be going like, well, you never told me that. That's right, I didn't. Why did I not tell you that? Because we aren't worrying about it. What is the name of that bond? It's a really hard name. It's a metallic bond. Okay? The characteristics go all sorts of haywire when we go into metal-metal bonds. Okay? So if you push really far into chemistry, say material science, okay, or any kind of material engineering, then you're going to be responsible for understanding what's happening between your metals, and you're looking at a slightly different bond situation. Yes?
Running like which one overrides the testing like sulfur and bromine, which one is more electronegative? And like sulfur is higher up, bromine.
That was a bad question on the test. Good point. If you look at the practice, because it was on the practice exam, right?
Yeah.
So on that practice exam, it had sulfur and bromide bound to each other. Okay, if we look at our trends, the higher up we are in our column, the more electronegative. Where's bromine? Underneath sulfur. Okay, so we would say bromine is less electronegative than sulfur, but further to the right on the periodic table, more electronegative. So according to that, bromine would be more electronegative. Well, you're kind of in this SOL situation. Which one is taller or higher? Okay. Yes, that was a big typo. What did I end up doing to fix that? I wrote up on the board the electronegativities of sulfur and bromine. That's how you would then have to answer the question, once you knew the actual electronegativities. The questions asked should be clear in their differentials, not in that weird gray area. Other questions? I thought maybe I saw a hand. Yeah.
So everything in the francium row and below is man-made?
Not everything. If you take a look at your periodic table, francium, radium, what is that? Actinide, thorium, Pennsylvanium, uranium. It's not Pennsylvanium. Don't quote me on that. Uranium. And then you run into all those white colored in ones. The white ones are all man-made. Okay. Other questions? Okay. So now we can really full on move into chapter 12, chemical bonding. I think we talked about this. We're looking at the sharing of electrons. Which electrons? The valence electrons, our highest energy level electrons. So if we're looking at our first two rows, or actually, sorry, our first row, how many electrons could be in our highest energy level for our first row on our periodic table? 2. How many valence electrons could be in our highest energy level for anything in our second row? 8. For our third energy level, what is the highest number of valence electrons? Careful. Third energy level has s, p, and d orbitals. As soon as we hit the third energy level, those d orbitals become available. Whether or not we put electrons into them becomes a separate question. Okay? We do have those available. So when we talk about Lewis rules breaking down, it breaks down right about at the third energy level. Okay? So we can get all sorts of weird things happening when we go beyond that. Does Lewis theory still hold for everything afterwards? Yes, it does. We have to make some tweaks to it. Do you need to worry about those tweaks? Nope. All you got to do is hold fast to the rules that we've talked about. Not all bonds are going to be the same. If we change the elements, we're going to get a different type of bond. Okay? The two main categories you're concerned about at this moment are ionic bonds and covalent bonds. Okay? Our ionic bonds are classified by metal and nonmetal. That is our very narrow definition. We should actually expand that ever so slightly. And I know Stephen here may remember why we need to expand that. It's not just metals and nonmetals, it's technically... It's fine. So let's pick an example here. Do you see a metal in this? That is an N, for those of you calling me out on that being a sloppy N.
No.
No metal. And you're still calling me out on a sloppy N. It's still an N. Okay. There is no metal. So according to the definition you just gave me for ionic bonds, can this be an ionic compound? No. Is it an ionic compound? Absolutely. So broaden your definition of ionic compounds. It's not just metals and nonmetals. It's cations and anions. When it comes to metals, what charge do our metals always carry? Which makes them cations. So our metals and nonmetals happen to be the largest class because 3/4 of our periodic table are metals, and they will always be positive. Okay? But realize we do run into these kind of subtle exceptions in our rule of thumb definition. Our covalent bonds, how do we know we have a covalent bond? Between two nonmetals, but isn't this all nonmetals? So between nonmetals that are not ions. Okay? So we have to be a little bit careful of those weird exceptions, but you guys should be able to nail those down. If we looked at these two compounds, water and HCl, we already talked about this. Okay? Both of those are covalent bond classifications according to our rules. So we might predict those to have the exact same types of chemistry because they both have the same kind of connectivity. Yet if you stick your hand in a solution of water, you're probably okay. If you stick your hand in a solution of HCl, you're probably not. Okay? So is there a distinct difference between bonds? Yes. So it isn't just ionic bonds and covalent bonds. That covalent bond category actually subdivides into other sections. Technically polar covalent and non-polar covalent. And we'll look at some examples of those. Actually, let's do it right now because we got it. So what we're going to evaluate is something about the reactivity characteristics of these two compounds. So let's simplify, and we're just going to look at one of those bonds, a bond to hydrogen and chlorine, and we'll look at the bond between hydrogen and oxygen. So at this point, I don't care about the other hydrogen and the other oxygen. It's going to have the same characteristics. All I'm looking at is these individual bonds and trying to come up with some prediction of their chemistries. What could I use to evaluate these?
Valence electrons?
Could use valence electrons. You'll find that's not going to help out too much. But not a bad choice. Could try and use our electronegativity. What does the electronegativity say? As a hint, the electrons in that bond are now being pulled one direction versus another. Okay. Which is more electronegative, chlorine or hydrogen? Chlorine. I know you're not going to like this, but I'm going to switch this to make it an easier example because it gets more come on. It gets a little bit more complicated than that. We'll go HCl, and we'll do HC. Okay. So those of you that wrote the O, just erase half your O, and you got a C. Okay. So, if we now look at these, which is more electronegative, chlorine or hydrogen?
Chlorine.
Chlorine. What does that mean happens to the electrons in that bond? They go towards the chlorine. Okay, you guys already looked at Lewis structures. I know we haven't reviewed it again yet, but when we did that, what happened? One electron came from the hydrogen, one electron came from the chlorine. Chlorine takes both those electrons. What happened to its balance of electrons? It's uneven. It's uneven in what way?
Unequal sharing of electrons.
Okay, true. So the chlorine becomes what? What's that? Becomes like the noble gas. What does that mean happened to it? It gained an electron, which means it becomes negative. The hydrogen would become positive. But if I show these as positive and negative, what have I just shown?
It's neutral.
Ions. Which means my bond is now, someone said it, an ionic bond. This isn't an ionic bond. So what I'm looking at is now the balance of the electrons within those and saying that the electrons are still being shared, but they're being shared unequally. Which means the chlorine starts to become negative and the hydrogen starts to become positive. But they are not formally positive and negative, which means I don't have an ionic bond. So I need to change this notation so that I can understand that this is not formally positive and this is not formally negative. Okay? So we could call it somewhat positive, somewhat negative. But if I had to go through and write somewhat every single time, that's going to get a bit tedious. So what did we come up with instead? We reference it as a partial charge. But if I had to go through and write partial every single time, that's still going to get obnoxious. So what do we do instead? Kind of a squiggly line, which is a delta symbol. What did we say deltas were used for previously? Change. What are we using it for in this context? It's the change in charge on our atom. The chlorine is changing to a negative. The hydrogen is changing to a positive. Has it done it yet?
No.
No. Hence the changing symbol. Okay? What happens if we look at hydrogen versus carbon? This becomes trickier. It may help to know the electronegativities that you all memorized, right? That was kind of a joke. Okay. We might still expect that carbon, being more electronegative than our hydrogen, would start to take the electrons and become negative, which would then mean the hydrogen would start to become positive. Okay. We can include our deltas. But evaluate the difference between those. In the case of hydrogen and chlorine, how large is that difference? Really big difference. So it's not a tiny delta. It's a really big delta. When we look at our hydrogen and carbon, how big is that difference? Really, really small. What does that mean? When I now compare the reactivity of these, I would expect HCl to react very violently because we have these massive charges, okay, or building charges. HC, relatively uncharged. Okay? So HC has already started to equate to a noble gas. Our HCl is now actually full-on pushed more towards the ionic end of the spectrum. At that ionic part of the spectrum, it becomes more reactive. Okay? It's just a neat little observation within this. This is known as your partial charge notation. To answer it, you have to know something about electronegativities. Okay? You need to know what element is more electronegative than another. That allows you to predict those differences. When it comes to the exam, if it comes down to something like this, which we did with the sulfur and the bromine, and you're like, well, I don't know those electronegativities, raise your hand and say, hey, stupid, you didn't tell me the electronegativities. Okay? You might say it a little bit nicer than that, but that's close enough. And I'll write the electronegativities up on the board for you. Okay? It may very well be an example where I'm like, nah, you should know that. Okay? because it'll be an extreme difference. Say cesium and oxygen. Okay. I picked the most electronegative element and the second most, sorry, I did that the other way. The most unelectronegative element in cesium and the second most electronegative element. You should know that trend. Okay. If it hits a gray area, that's fine. Ask about it. Questions? I'm assuming the head shaking yes means no questions. I'm just checking. Okay, in our ionic bonds, cations, anions. Anions are typically nonmetals, cations are typically metals. You get these very regular shapes. Okay. What happens to the ionic radii when we go through and make a cation and anion? So if we take a sodium atom and we bond it to a chlorine atom, we would get sodium ion and chloride ion. What happened to the sodium to go from sodium atom to sodium ion? It lost an electron. So what happens to its size? It shrinks. Okay. At best, it should look like the electron size for neon. Okay. It's actually going to be a little bit smaller than neon. Why should it be smaller than neon? It has more protons. Okay. What happens to the chloride? It should get bigger because I'm now adding electrons while not changing the number of protons, so it gets bigger. The result is I see a swap in the size of those atoms. Okay. If we want to look at the bond length in the case of an ionic compound, what's going to be our approximate bond length? It'll be the distance from the center of one bond to its outside, and the distance from the center of the other bond to its outside. You're looking at the sum of the radii. Okay. Whoops, that went faster than I wanted. Questions on that? Take that as a note. What should happen with covalent bonds? Well, in covalent bonds, we actually have a sharing of electrons, which means if I take those two spheres, so in an ionic bond, I took my two spheres and I brought them near each other. Okay, one gave up electrons, so it got smaller. The other one gained electrons, so it became bigger. Okay. But that's all that happens. What happens with a covalent bond? We now bring them to each other, and what happens? They share electrons. For them to share electrons, those orbitals where the electrons exist must overlap. If they do not overlap, we cannot get a bond. Which means what happens to the bond length in a covalent compound? It's now no longer the sum of the radii, because the radii then assumes that they are not overlapping. If we overlap them, what happens to the bond length? It shrinks ever so slightly to maximize the overlap between the orbitals. When we go through and look at our distances, you'll notice that that is indeed what happens. Okay. If we just add up our radii, we get 0.136 nanometers. If we look at the actual bond length in HCl, 0.127. It's a little bit smaller. Why? Because I'm making a covalent bond. Those electron clouds must overlap, which means they have to get closer than the radii allow. Kind of, sort of?
So what you said before was just wrong?
What do you mean what I said before?
About adding the two radii together.
Okay. Adding the two radii works for ionic compounds because in ionic compounds we aren't sharing electrons. It's a transfer of electrons. In covalent compounds, our rule changes because we are now changing the bond characteristic. It's now a sharing of electrons, which means our bond length is going to change, the distance between those nuclei.
So how do you know the bond length?
How would you actually calculate the bond length? Okay. For the sake of a covalent compound, all you would be able to do is add the radii and say it is less than that number. That is all you have the ability to do. Okay. If you would like more than that, talk to somebody other than me, because I don't know. Do you have a question, or is it the same one? Okay. Questions? Bond energy. This is a crazy concept. Okay? So let's think about it at first. All reactions either absorb energy or release energy. Okay? Do bonds exist in nature? Yes. So we know this is something that happens. Okay? When we look at all of our reactions and think about the world around us, we are moving from a high energy state to a lower energy state. Everything like that is happening. So when we go through to look at our electron configurations, our first electron went where? The 1s. Why the 1s and not the 2s or the 3s? Lowest energy. We are always striving for that lowest energy possible. Which means if I'm now going to look at the possibility of forming a bond between the two labeled now nitrogen atoms to form this product, okay, would I expect the energy of my product to be lower or higher than the start? Okay. All reactions strive for lower energy. If I predict there to be a valid bond, the bond or the molecule there should be lower in energy than our starting material.
Right.
If it is higher, what does that mean about the likelihood of forming the bond? Not very likely. How can I add that energy term to my equation? What happened to that energy? I can't create or destroy it. And if somehow the energy of my product is lower than my energy of my reactant, I have to account for it somehow. Okay, one suggestion was plus heat. And the plus heat goes on the product side. Why on the product side? If my product is lower in energy, where did all that energy go? As heat. It was released. It's no longer in the chemical bond. So I would get a release of heat. If I put it on the other side of the equation, I'm saying I have to add heat to get those to form a bond. Right? Which goes counter to what we just said about the formation of a bond. So this means every time we form a bond, it is a release of heat, which is also known as an exothermic reaction. I know, fishing for a big term there. Okay. What if I break a bond? Ooh, that's tricky. I'm now doing the reverse. So let's draw that out. If I take now my bond, and I now run the reverse, what would I expect? To get this reaction to go, where's the heat term show up? On the reactant side. I have to add heat to get the bond to break, which means this reaction is now endothermic. Why does the heat change sides? That may be a bit odd, so let's try that again. Why did I change the side with the bonding molecule? Because I'm doing different things. I'm breaking the bond. So I'm taking the bond and putting it onto the reactant side. What did I do with my reactants, my old reactants? I made them my new products. Did I make just one of them a new product? I made both of them new products. Well, if I move both of my reactants, what should I do to both of my products? Also transfer them. By inputting heat as a term within your reaction, you can go through and interpret the heat a little bit easier, get to your endo and exothermic situations a little bit better. Okay? That heat term is what is known as your bond energy. Okay? We will only classify it for covalent bonds. Are all bonds the same? We've already talked about ionic and covalent, but you'll notice I've added this extra term. This is our polar covalent. You notice I used HCl versus HH. How can I subcategorize these so that I know which one's which? How do I know when I look at NaCl that that's an ionic bond?
Sodium's a cation.
Sodium is a cation. It is a metal and a nonmetal. How do I know when I look at HH that that is a covalent bond? There's no metal. So it's two nonmetals, which I'm going to abbreviate NM and NM. We run into an issue here. What's that issue? How do I distinguish between the nonpolar and the polar? Okay, we don't have a way to distinguish at this point. Look to the right of each of those terms. What shows up? This little parenthesis thing with a number in it and some greater than, less than arrows. Any ideas what that number is in reference to? The difference in electronegativity. If you have a large difference in electronegativity, a difference greater than 1.7, that is an ionic compound. All of our metal-nonmetal bonds generate an electronegativity difference like that, most of them. Okay. Our nonpolar covalent is the only other one that you see show up there. I'm saying less than 0.5 for a difference. Okay. How many of you memorize the electronegativities? Nobody? Okay. I didn't memorize them either. So we need a better way to determine the difference between nonpolar covalent and polar covalent. Okay. We're looking at a difference less than 0.5. Is HH going to be a nonpolar covalent bond? What is the electronegativity? I don't know. Thank you for that. What is the electronegativity for hydrogen? I can get another, I don't know, pick a number. I don't care what number. Magic number. Give me a number. 1. What is the electronegativity for the other hydrogen? 1. What is the difference between 1 and 1? Less than 0.5. A way to be extra specific on that. Which means the bond between anything bound to itself is nonpolar covalent. That says anything to itself. That definition is a little bit too narrow for us, so we include one more bond classification to help us out as a rule of thumb. Ultimately, it comes down strictly to the differences in electronegativity. Okay? But we don't want to memorize those. For your homework, you should probably look them up. Use my little rules of thumb first, and then look them up and see how close you were. You'll find out you're really close. On the test, I expect the rules of thumb. The one extra rule that you need to know for a nonpolar covalent compound. Hydrogen bound to
Helium.
S.
What was that? B. Yes. Oh, let me add an extra line. Hydrogen bound to carbon is the only other nonpolar covalent bond. Okay. Notice I said only other. So we've got a rule for ionic, metal, nonmetal. We've got rules for now nonpolar, anything to itself, and hydrogen bound to carbon. What is left over? Beautiful definition. Everything else. This quickly allows you to classify the different types of bonds. Once you know the types of bonds, you can then start to predict something about their chemistry. Organic chemistry, for instance. Okay? So having these rules memorized will help you. I think it is important, so I continue to ask questions about it. It even shows up in my second semester organic chemistry class. In fact, I've even thrown it on a biochemistry class test, okay, on just what is the definition of the individual bonds. Understanding what is happening within your atoms makes a huge difference on how those things can interact with other stuff. Okay. After that, we move into our Lewis structures. Okay. In theory, you all watched that video, so I'm not going to talk a whole lot about this except for one big classification. Lewis based everything off of 8 electrons because he simplified and looked at the first 2 rows for bonding, which meant 8 electrons. He thought, what shape has 8 electrons? Cube. Everything he drew in his initial paper, I did actually look it up, was with cubes. Yes, it looked awful, okay? But that's where it came from. We simplify that. Instead of saying cubes, that's an ugly thing to go through and draw, we instead converted that into squares. So that when we go through and draw in a Lewis structure, actually, I'm going to shift the next screen. Whoops, that was a bad idea. I'm not going to shift to the next screen. If we picked the Lewis structure for, say, CH4, carbon is our center atom, we then scatter the other elements around the hydrogen. And you'll almost always notice that we scatter elements in this fashion. People go, well, why did you order it that way? Couldn't you have just as easily done it something like this? Yes, you absolutely could have. Why did I organize it the way I did? I have placed those other atoms on the face of the square of my center atom. In the other case, it's the same deal, but I've now turned my square on edge. It becomes more confusing to look at. All of the Lewis structures that you are responsible for are based off of a square. So when you are asked for groups of electrons, you look at the faces of a square. How many faces are there on a square? Which means how many groups of electrons can you possibly have? 4. There are only 4 faces on that square. Okay? I can put 50 million electrons on one face. That is still only one group of electrons. Okay? I could put 1 electron on a face. That is now one group of electrons. Okay? So, the rules. Your textbook uses different rules. You will get to the same answer except when it comes down to resonance. 9 times out of 10, I notice that when it comes to resonance, particularly as it's taught in the tutoring center as well, students ask, well, why is there resonance? You go, well, you could have just done it this way. What do you mean I could have just done it this way? You mean you knew the answer, and you're now telling me there's 2 answers because you know there's resonance. Yeah, that's what they're telling you. Okay? It doesn't work that way. If you follow these rules, resonance naturally falls out. Okay? And I know that sounds weird. You're like, I follow those rules. That kid's a liar. No. Let's look at a couple examples. Let's pick CO2, because that was on your worksheet. Wasn't it? Okay. And in that activity, I said that there were 3 structures that had resonance. What did the sub tell you you had? They could only find 1. Huh, that's fascinating. Why? Number 1, she's not an organic chemist. Number 2, she followed rules that are not in the textbook. She followed rules according to what she knew the answer to be accepted to be. When you follow answers or follow a logic to getting an answer by knowing the answer, you've defeated the point of solving it to begin with. Okay? So, let's evaluate beginning to end. First step, total valence electrons. How many electrons does carbon have? 4. Okay, it has 6 total electrons. Thank you for saying the 6. We only want the valence electrons. It has 2 core electrons in the 1s orbital. I don't care about the core because when we form a bond, what electrons interact? Only the outermost electrons. That's our valence. How do we know carbon has 4? What column is carbon in? The 14th column or 4a. Either way, you get 4. Oxygen has 6. There are 2 of them, so I must multiply by 2. I have to count the electrons from every single atom, which gives me a total of 16. Next rule, pick the center atom. Your center atom is the least electronegative that can bridge. Right? This is where knowing your center atom or your electronegativities can help. Which is lower in electronegativity, carbon or oxygen? Carbon, which means carbon is the center atom. Right? If you don't like electronegativity, you can use metallic character. I only use electronegativity, so the most least thing starts freaking me out, and I end up goofing it all over the place when it comes to metallic. So I'm just going to take that as a wash right now, and you can talk to me after class. Okay? I now want to go through and add the rest of my atoms around that center atom. Does it matter where I place them? Not for Lewis structures, because the biggest flaw with Lewis structure is it does not explain shape. So it does not matter where I place the oxygens around the center atom as long as they are placed around it. Okay? Most people would probably place oxygen and oxygen. Why? Symmetry. Okay? Lewis does not account for that, so let's make sure to make it look goofy. Let's put it over here. Okay? I am still placing the atoms on the face of my square for my center atom. What's the next rule? Add electrons where? The most electronegative atom. In this case, that is an outermost atom. Will it always be an outermost atom? No. That's why the rule is there. It's not outermost atom, it's most electronegative. Okay? Because depending on the structure, you may end up finding that you'll need to put it on the center atom first. So we will add electrons to our our most electronegative oxygen. Is there a difference between either of those oxygens? No. So don't artificially make one. Okay? Just pick. Let's say the bottom oxygen. How many electrons should I put around that bottom oxygen? 8. Whoever said 6, okay? I apologize for calling you out on it. But the 6 comes from its valence count. I do not care about valence electrons anymore. I care about octets. Okay? I do not put 6 around any atom. I put 8. Okay? So I will start putting electrons around my oxygen, and I will put them in pairs around that oxygen atom until I have my 8 electrons. Okay? I need to put 16 into the structure. I've only accounted for 8, which means I need to find another place to place electrons. Okay? So where's another place? Why the other oxygen and not the carbon? Oxygen is more electronegative than carbon. So you continue to go through and place electrons around your most electronegative. As I add those around, I have now added my 8 electrons around my oxygen, and I now have a total of 16 electrons. Next step. Okay? Convert pairs into lines. So by pairs, we're referring to bonding pairs. How do I know it's a bond? It's between atoms. Right? That's when we form a bond, when we have electrons between atoms. If we don't have electrons between atoms, we don't have a bond. Right? So I will go through and place my bond there. Whoops, need that space later. And there. Okay. Step 6, satisfy octets by moving pairs of electrons. So this implies a couple different things. Number 1, check to make sure everything has its octet. If you are missing an octet, start moving electrons around. How many electrons around this oxygen? 8. 2, 4, 6, and I can count the electrons in the bond. 8. How about the bottom oxygen?
8.
2, 4, 6, 8. I've got 8 electrons around the bottom oxygen. How about the carbon? Only 4 electrons. Notice that I am again counting those electrons twice. That's fine. Okay? All we're looking at is how many electrons does any individual atom have near it. Carbon has access to 4 electrons. Okay? We call it the octet rule for a reason, because we need 8 electrons. We are now moving into this resonance option. Okay? I have to move electrons. Where do I have electrons? On an oxygen. Which oxygen do you want to look at? I heard the bottom one. So I'm going to move this pair of electrons to the carbon. Well, now carbon has 2 more electrons, but what happened to the oxygen? It's now lost 2 electrons. So it's not just picking up and moving to atom. I have to move them in such a way where those electrons are now shared between the atoms. Meaning I have now generated another bond. So I can show a line. As referencing whether it's single, double, or triple. Well, how many lines are there? 2, which makes it double. Does the carbon have its octet yet? No. So what do I have to do? I need more electrons to that carbon. Where do I have electrons? The oxygen to the right has electrons. So does the oxygen to the bottom. Which means I can take from either of them. Which means resonance. If you just draw out the answer as you know it to be, you do not find this resonance structure. Okay? Why do they know it to be something else? Because the resonance structure you're drawing is horrible. Doesn't make it any less valid. It's still correct. It's just a bad resonance structure. Okay? So your other option is to move a pair of electrons from that same carbon or that same oxygen, and we now have a triple bond. Okay? You may be freaking out, oh, wow, you can't do that. How many electrons are on the bottom oxygen? 8. How many electrons are on the carbon? How many electrons are on the other oxygen? All of our rules are satisfied. Guess what you just drew? A perfectly valid Lewis structure. Your other options for this case. Sorry, it's a little crowded there. We've got showing the triple bond in the other direction, and we also have this case. Any way you slice it, all of the answers come out the same, even when it comes to shape. Okay. Do you have the ability, looking at these 3 structures, to say which of these, whoops, sorry, I started getting that bad habit. Let's maintain the same shape. Okay. Do you have the ability to decide which of these 3 is the best one? Kinda, sorta. Particularly if we now move into shape, we could say how many groups of electrons are now around our center atom. Does it matter which of these resonance structures we look at? No. They all have 2 groups of electrons around the center atom. Are those groups different? Yes. Is that relevant? No. We look to the bottom face. Are there electrons there? Look to the left face. Ooh, that gets really crowded there. Top face. Right face. How many faces have electrons? 2. Which means the electron geometry is linear. Okay, those of you going, holy crap, how do you say that answer so fast? You memorize the table that I gave you. It's kind of important. It tells you how to do it. Okay? If you don't have that memorized, you can't come up with these shapes. Okay? What would the molecular geometry be? Well, now you go through and look at those same groups of electrons and decide, are those bonding groups or non-bonding groups? Well, in the case of our structure that we've already drawn in, we only have lines, which means we have bonding groups. So we have 2 bonding groups and no non-bonding groups, which means the shape is linear. Okay? So let's redraw these structures. Am I allowed to redraw, erase all this? Okay. So let's redraw this to better reflect the shape of the molecule. So there's one of our options. And I didn't forget your hand. I did see you. there was our other option. We actually have the third, which is just the reverse of the top one. Okay. Which of these two is better? The bottom one, because symmetry. Okay. There is a better answer than that, but you're not responsible for it. That's the line through one. That's step 7. Okay. You aren't responsible at that point yet. Both of those structures are valid. You should be able to achieve both of those on a test. Technically, all 3 of those. You should show all 3, particularly if the question is being vague and just says provide the Lewis structures. Technically, I've only got 2/3 of the answer here. Okay, 1, 2.
Answer my question is, the top one, when you
Yes.
flip-flop the bonds,
Yes.
isn't it just the same structure rotated? I mean, is it still considered?
Yes, and so this is where resonance becomes weird. Okay? When we look at resonance, your structure is pinned. Okay? Imagine it like cutting open a worm, because worms have heads and tails, right? Okay? So if you filleted a worm and pinned it down, if you turned it around, are you now looking at something different? Yeah, the head is now on the left versus the right side. Same thing's happening here. Okay? Yes, it's a weird concept, but it's relevant for resonance. He had the question, huh?
I think so.
Good timing. Okay. Hopefully we'll get back to his question later. Questions about this? Okay. So Lewis structures in reality leads us to Vesper. You've got all these different shapes and stuff that can come out of it. Ultimately, what you need to be able to do, come on now, whoops, is interpret this chart for any given structure. All right. I said I was going to do a couple more examples, but I want to leave this up here. So unfortunately, if you're watching it at home,